Fundamentals of HVACR, Chapter 12, the Refrigeration Cycle. Objectives include: explain the fundamental principles behind the refrigeration cycle and identify the system's four major components. Identify where in the refrigeration system the refrigerant is saturated, superheated, or subcooled. Draw a basic compression refrigeration cycle and identify the pressure, temperature, state, and heat content in and out of each component. Name the three main refrigeration system interconnecting lines. Describe how refrigerant is stored in the refrigeration system. And describe optional components in the refrigeration system. A thorough understanding of the refrigeration cycle is absolutely essential to working in the HVACR field. The mechanical compression cycle is used in a wide range of applications, including air conditioning, commercial refrigeration, and industrial process cooling. The refrigeration cycle has four main components: the compressor, the condenser, the expansion device, and the evaporator. The compressor compresses or squeezes the gas into a smaller volume. The high-pressure, high-temperature superheated gas travels from the compressor to the condenser. This is where the heat is rejected from the refrigeration system. The condenser condenses the refrigerant from a high-pressure, high-temperature superheated gas to a high-pressure, warm, subcooled liquid. The high-pressure, warm, subcooled liquid travels to the expansion device, also called a metering device. The expansion device drops the pressure and temperature of the refrigerant by restricting its flow. The refrigerant is now a low-pressure, low-temperature, low-heat, saturated mixture. At the same time, the refrigerant is passing into a larger space and expanding. The combination of the pressure drop and the expansion dramatically drops the temperature of the refrigerant, and it starts to flash off to a vapor. The evaporator is the component that cools by absorbing heat from its surroundings. The low-temperature saturated mixture enters the evaporator, where it evaporates from a liquid to a gas, absorbing heat. Now let's talk through the cycle and put a little more meat on the bones. In addition to the general descriptions, we'll add actual pressures and temperatures. It is important that you understand these pressures and temperatures are not chiseled in stone. They change with a lot of different variables. But using actual pressures and temperatures may help you get a better handle on what's happening. The refrigerant enters the compressor as a low-temperature, low-pressure, superheated vapor. Superheating is a process of continuing to heat the refrigerant after sufficient latent heat has been added to vaporize all the liquid. Superheating ensures no liquid slugs will reach the compressor and cause damage to the compressor. Compressors are really designed just to pump vapor. This is because they squeeze what they compress. Liquid doesn't squeeze. If you try to squeeze liquid, something will break. In our example, the vapor is 118 psig and 50 degrees Fahrenheit. This makes the gas superheated because its saturation temperature at 118 psig is 40 degrees Fahrenheit, so the actual measured temperature is 10 degrees warmer than the saturation temperature. The refrigerant leaves the compressor as a high-pressure, high-temperature, superheated vapor. The refrigerant contains both the heat absorbed in the evaporator and the heat of compression from the compressor. In our example, the pressure is 365 and the actual measured temperature is 160. This makes it superheated because the saturation temperature at 365 is 110. The refrigerant entering the condenser is at the same condition as it was leaving the compressor, superheated. The first portion of the condenser is used to reduce the temperature of the refrigerant to the saturation temperature. This portion of the condenser is often referred to as a desuperheating section. In our example, it's 365 psig, 160 degrees Fahrenheit, which makes it superheated because the saturation temperature at 365 is 110. Once the refrigerant temperature is reduced to 110, any additional heat removed will cause condensation. This is latent heat. During this time, the refrigerant temperature remains stable. The saturated refrigerant mix has a pressure of 365 and its temperature is 110. The refrigerant is all liquid in the lower portion of the condenser. The temperature of the liquid refrigerant is reduced as heat continues to be expelled to the surrounding air. This portion of the condenser is called the subcooling section. The subcooled liquid is still 365 psig, but now it has a temperature less than 110. In our example, the 365 psig refrigerant has been cooled to 100 degrees Fahrenheit, which is less than the saturation temperature of 110, so the refrigerant is now subcooled. The refrigerant entering the metering device is essentially the same condition as it was leaving the condenser. The refrigerant is a high-pressure, warm, subcooled liquid. In our example, the pressure is 365 and the temperature is 100. Since the saturation temperature is 110, the refrigerant has been cooled below the condensing temperature, making the refrigerant subcooled. The refrigerant leaving the metering device is a much lower pressure and temperature. In passing through the metering device to the low-pressure evaporator, some refrigerant is evaporated, cooling the remaining liquid. The refrigerant is typically a mixture of 75% liquid and 25% vapor at this point. In our example, the refrigerant is at 118 psig, 40 degrees Fahrenheit, which is a saturated mix. The condition of the refrigerant in the middle of the evaporator is very similar to the condition entering the evaporator. 118 psig and 40 degrees Fahrenheit saturated mix. Heat from the air or product being cooled in the evaporator is absorbed by the liquid refrigerant and causes the refrigerant to boil or vaporize. The refrigerant mix in the center is now closer to 50% liquid and 50% vapor. The refrigerant is superheated leaving the evaporator. Superheated refrigerant ensures that liquid refrigerant does not enter the compressor. The refrigerant is now 118 psig and 50 degrees Fahrenheit, which is 10 degrees higher than the saturation temperature for that pressure. Subcooling the liquid refrigerant increases system efficiency by reducing flash gas and increasing mass flow. The compressor is a mechanical device for pumping refrigerant vapor from the low-pressure evaporator to the high-pressure condenser. The main types of compressors are reciprocating, rotary, centrifugal, screw, and scroll. Heat travels from hot to cold. The two factors that affect the amount of heat transferred between two objects are the temperature difference between the objects and the mass of the objects. Temperature difference is what allows heat to flow from one object to another. The greater the temperature difference, the more rapid the heat flow. Increasing the coil size and the amount of refrigerant in the coil also increases the rate of heat transfer, which reduces the condensing temperature. Less energy is required to produce the lower condensing temperature, improving system efficiency. That is why the new higher SEER outdoor condensing units are significantly larger than older models of the same capacity. The same principle has been applied to the evaporator coils of the new high SEER systems. This slide shows a comparison shot between two condensers with the same cooling capacity, 2 tons. However, one is more than twice as efficient as the other. The condenser really has 3 sections. The first portion of the condenser cools off the superheated gas and lowers its temperature to the saturation point. This part of the condenser is called the desuperheating section. When the temperature of the vapor reaches the saturation temperature, the additional latent heat removed causes condensation of the refrigerant, producing liquid refrigerant. This is what is happening through most of the condenser. The end of the condenser subcools the refrigerant, lowering the refrigerant temperature below its saturation point. This is called the subcooling section of the condenser. There are three types of condensers: air-cooled, water-cooled, and evaporative. Air-cooled condensers can be divided into three general types: natural draft, forced draft, and induced draft. Natural draft condensers do not have fans. They rely on natural air currents for air movement across the condenser. An example would be a small refrigerator. Forced draft condensers use a fan to force air across the condenser. In a forced draft condenser, the cups of the blade will be facing towards the coil, so the fan is pushing air across the condenser. Induced draft condensers use a fan to suck air across the condenser. In an induced draft condenser, the cups of the fan blades will be facing away from the coil. The types of water-cooled condensers include tube-in-tube or double pipe, shell-in-tube, and shell-in-coil. In all water-cooled condensers, the water and refrigerant flow in opposite directions. This counterflow design provides the best heat transfer by ensuring a good temperature difference between the two fluids. Counterflow condenser design ensures that the warmest refrigerant is against the warmest water and the coldest refrigerant is against the coldest water. A double pipe condenser uses a tube inside a tube. Double pipe condensers can be a single circuit using a continuous loop or several parallel pipes forming a multiple circuit. In either case, the water and refrigerant should flow through the condenser in opposite directions. This is called counterflow. Single-circuit double pipe condensers can be constructed using a tube inside a tube or two tubes beside each other wrapped in a protective outer tube. Tube-in-tube is more efficient, but is more likely to allow water in the refrigeration system should a leak develop in the inner tube. Tube beside a tube protects against cross-contamination in the event of a leak because there are two walls between the refrigerant and the water. Shell and tube condensers can be either vertical or horizontal. Shell and tube condensers also act like a liquid refrigerant receiver because liquid refrigerant accumulates in the bottom of the condenser. Evaporative condensers use water evaporation to help cool the refrigerant. Evaporative condensers require more maintenance than air-cooled systems because the warm, open water sump is a perfect place to grow bacteria, mold, and fungus. Also, evaporation causes mineral scale to build up. If the scale is not removed, the condenser's efficiency will drop. The expansion device controls the flow of refrigerant to the evaporator. It separates the high and low pressure sides of the system. Two actions occur in the expansion device. One, the pressure of the refrigerant is reduced to a pressure corresponding to the evaporator temperature at the saturated condition, and two, refrigerant liquid is cooled to the evaporator temperature by actual evaporation of some of the liquid refrigerant. There are two major types of metering devices commonly used in modern refrigeration systems: fixed bore expansion devices and thermostatic expansion valves. Fixed bore expansion devices limit the amount of refrigerant that can pass through the restriction, reducing the refrigerant pressure and temperature. The pressure difference across a fixed bore expansion device affects the refrigerant flow through it. A higher pressure difference produces more refrigerant flow. Lower pressure difference produces less refrigerant flow. Thermostatic expansion valves are designed to maintain a constant superheat by adjusting to varying load conditions. The pressure from the sensing bulb is balanced by the evaporator pressure and the adjustment spring pressure. The sensing bulb pressure tends to open the valve as the suction line temperature increases. The evaporator pressure tends to close the valve as the evaporator pressure increases. The evaporator is a device for absorbing heat into the refrigeration system. In the evaporator, the saturated refrigerant absorbs heat from its surroundings and boils into a low-pressure vapor. The vapor refrigerant is then superheated at the end of the evaporator. There are three general types of evaporator construction: bare pipe, finned tube, and plate. On finned tube evaporators, the tubing is interconnected by aluminum fins. Fins serve both to direct the airflow through the coil and increase the heat transfer by increasing the surface area of the evaporator. The fin spacing on an evaporator is partly determined by its intended operating temperature. Evaporators that constantly operate below freezing have wider fin spacing, so frost accumulation does not interfere as much with airflow. Evaporators that typically operate above freezing can use closer fin spacing because frost does not accumulate. The components of the refrigeration system are connected by three refrigerant lines: the discharge line, the liquid line, and the suction line. The discharge line carries the high-pressure, hot, superheated gas from the compressor to the condenser. It is called the discharge line because refrigerant is discharged into it from the condenser. The discharge line is the smaller of the two lines connected to the compressor. The liquid line carries high-pressure, warm, subcooled liquid from the condenser to the metering device. On a split system, the metering device would be inside. The liquid line is the smaller of the two lines connected to the outdoor unit. The suction line is the larger of the two lines connected to the compressor. The suction line carries the low-pressure, cool, superheated vapor from the evaporator coil to the compressor inlet. The capacity of many refrigeration systems will vary depending upon the operating conditions. Capacity changes also produce different refrigerant flows. An increase in refrigeration capacity circulates more refrigerant. A decrease in capacity circulates less refrigerant. Some form of refrigerant storage is necessary to facilitate capacity changes. Liquid receivers are a way to store refrigerant that is not being circulated in the system. The liquid receiver is located at the end of the condenser outlet to collect liquid refrigerant. The liquid receiver allows storage of liquid refrigerant until it is needed by the metering device. An accumulator is both a storage device and a safety device. The accumulator is located in the suction line just before the compressor. Its purpose is to prevent liquid refrigerant from returning to the compressor. The accumulator allows both vapor and liquid in, but only vapor out. The inlet side of the accumulator is connected to the outlet of the evaporator. The outlet of the accumulator draws vapor through a U-shaped tube or chamber to allow the vapor to pick up any oil that is trapped in the accumulator. Other refrigeration components may be found on a refrigeration system to protect it, improve its efficiency, or help it meet the needs of a special application. The functions of each of these are covered in more detail in Unit 18, Special Refrigeration Components. The mechanical vapor compression refrigeration cycle is the most common of all refrigeration cycles. The four main components are the compressor, the condenser, the metering device, and the evaporator. The refrigeration cycle is made possible by the pressure difference, which is maintained by the compressor and the metering device. The compressor increases refrigerant pressure by squeezing it. The metering device reduces the refrigerant pressure by restricting its flow into the evaporator. The low side absorbs heat when the refrigerant boils in the evaporator. The high side rejects heat when the refrigerant condenses in the condenser.